While thinking about spiders and their web, I remembered that their web is incredibly strong. When I was young, I used to dream about making super strong ropes out of their web, and the dream just came back, but with different intentions. Now, I wonder, is cable made of spider silk the key to a space elevator? To start, I begin by researching the space elevator, finding that the largest problem is finding a material strong enough to withstand the massive amount of force of tethering something from space to Earth. I dug into finding what the current best contestant for the tether would be, finding out that the most common idea is nanotubes. I then looked into exactly how strong carbon nanotubes are versus how strong spider silk is, and found that the nanotubes to be much stronger. Although spider silk does not appear to be the answer to a space elevator, it did get me wondering why spider silk is such an incredibly strong material. Why are spider webs so strong? I think that a vital part of what makes a spider web so strong is its ability to stretch and return to its original length, seemingly unharmed. This can be observed by watching a spider's web in strong wind, or even if we pay particularly close attention to a struggling insect in the web. The insect will do its best to escape, but regardless of how far the bug's legs can move, the web will stretch with it, either entangling the insect further or just returning to its original length. Other contributing factors to the strength of silk include what it is made of and the structure of the threads. I think that the strands could be made of two types of material, the inner layer being very difficult to break from force, while the outer layer being a sort of shield to protect the inner layer from the elements, similar to climbing rope. As I dig deeper, I find that the spider silk is even more complicated than I originally imagined, and there are many different types of silk with different purposes. I find that because the silks are so diverse, the majority of research on spider silk is done on the drag line, which is the strong cable of silk used by spiders to lower themselves and for structural support in their webs. While there are a whole bunch of different types of silk spiders can produce, we do not even really have a solid understanding of the molecular structure of spider webs, although we do know them to be made up of proteins that are made up of amino acids that have kept a stable sequence over long evolutionary periods. Because the silk is not made up of something that is particularly strong on its own, it must be the structure that the materials are put together in that gives the silk its incredible strength and elasticity. The spider silk manages to be so elastic and strong because it alternates pseudo-crystalline structures with elastic segments, giving it both stretch and strength. Having a structure that allows for elasticity is important for spiders because it allows their webs to absorb the force of them falling, or flying insects running into their webs over a longer distance, reducing the initial impact. While spider's silk is very strong for its weight, it is still meager in comparison to carbon nanotubes, and therefore is not the answer for a space elevator cable. Even though it might not be the answer to helping us get off the planet, the silk from arachnids is starting to become more and more feasible material to use because scientists are discovering ways to produce spider silk from different organisms, such as domesticated silkworms through genetic modification, as is seen by Craig Biocraft laboratories. With a super strong biological material like spiderweb transitioning from impossible to fairly cost-efficient to produce, it makes me wonder, what's the next step on the frontier of bioengineering?